Hello students, and welcome you all again to this video lecture series on chapter mechanical testing of materials or mechanical testing of metals. In last lecture we have seen what are the various tests. There is destructive and non-destructive test to be performed for the finding properties of metal or finding defects in the metal. And then we have seen the difference between these destructive and non-destructive testing methods. Today in this video we will see the first destructive testing method, that is tensile test, for finding various properties of a metal. So firstly we will see why the metals are tested. To ensure the quality of the product, we need to test the metals, again to test the properties, to find out the properties of the metal so that those can be used in the actual application after finding the properties. Next, to prevent the failure in use while actual applications, whatever loads which are applied on the final application, so these can be predicted and we can prevent the failure after prediction of these final loads. Finally, to make the informed choices in using the materials. So whatever changes in the material in the application that we can do based on the properties of the metal which are got after testing of the metals. So for these purposes we need to test the metals. After finding or after testing the material, we can find the properties of the metal such as strength, hardness, ductility, brittleness, toughness, etc. So by using destructive testing methods we can find all these properties such as a tensile strength, hardness, impact strength. We can find out the creep, we can find out fatigue, we can find out the brittleness, we can find out the toughness also. So for finding these properties we need to do destructive testing methods, and from that today we will see the first method, that is a tensile testing method. So in tensile testing method, it is the way of determining how something will react when it is pulled apart. When we are applying the pulling force on the metal, so how it behaves when the force is applied uh, in the tension manner. So that is nothing but a tensile test. It is one of the simplest tests and most widely used in the mechanical test to find out the various properties of the metal. So various properties of the metal can be found by using this tensile test. By measuring the force required to elongate a specimen to breaking point, material properties can be determined that will allow the designer and quality manager to predict how the material and products will behave in their intended application. So depending on this behavior of the metal, that applications will be decided and those metals can be used in the actual applications. So for that purpose this tensile test is very important. So why this tensile test is performed on the material? So whenever you are choosing the material to serve any of the application or any of your purpose, you would have to know a certain properties of the material. For example, you would want to know how the material behaves under tension, how the material behaves under compression force, how much load the material can bear before getting fracture, that means before getting breaking. So will it be brittle or ductile? How much of the energy it can absorb before the failure? How much of the energy it can absorb before failure is nothing but a toughness. So what is the toughness of that material? Uh, till what load it will be showing the elastic properties. So what is the its elastic limit? That also we want to know. After how much load the deformation will be permanent, that means what is its plastic deformation? In what range the load should be applied so as the material is not harmed, so that the material will not break? How strong or weak the material is, or that is nothing but how much stress is required to produce a given strain. So all these properties can be determined by doing the tensile test on the material only. So for that purpose we will study here the tensile test, and in tensile test all these properties such as a toughness, elastic limit, plastic deformation, uh, again what is a fracture point, whether a material is ductile or brittle, what is its tensile strength, what is its yield strength, what is its ultimate tensile strength. All these things we will find out by using this tensile test. So before starting the tensile test, actual tensile test, we will first understand what kind of loads are acting on the material and what is stress and what is strain, because those things are useful in the tensile test. That's why we'll study this. So firstly, the normal load or axial load is acting on the component. The load is perpendicular to the supporting material, is nothing but a normal load. During the normal load, that may be a tensile load or compression load. In tensile load, as it material as the ends of the material are pulled apart to make the material longer, the load is called as a tensile load. And as the ends of the material are pushed in to make the material smaller, the load is called as a compression load. So in those two figures, tension and compression loads are shown. Whenever the material is pulled away, then that load is called as a tension load. Whenever that material is pulled towards, the ends are pulled towards each other, then that load can be called as a compression load. Again, there will be a shear load. Shear load is nothing but a tangential load. We are applying the load in the tangential manner so that that component will fail in the shear manner. So that is also one kind of load. So tensile, compression and shear loads are there. If these are the loads, then one more thing is there, that is stress and strain. So what is stress? Stress is nothing but a force per unit area, or you can say it as a load per unit area. In order to compare the material, you must measure the stress and strain properties. Those are required in the tensile test. So stress is nothing but a force per unit area, and strain is nothing but a it is the ratio of change in length to the original length, or it is the ratio of elongation of material to the original length. And what is elongation? Elongation is nothing but a change in length, and the change in length we can calculate by that last formula is there of elongation, nothing but a change in length. Final length minus initial length, you can find out this elongation, and elongation is nothing but a change in length. Final length minus initial length, you will get the change in length. Change in length is nothing but elongation. Therefore the strain is equal to elongation divided by its original length. So this is about stress and strain. These two properties are there whenever we are applying load on a component or load on a metal or force on a metal, then that metal will undergo for these two things, that is stress and strain. Stress is nothing but, for suppose this square, or this rectangle metal component is there and we are applying a force in tensile manner. So along this cross section A we are applying this force, therefore stress will become, and stress is represented by sigma. That sigma stress is equal to force upon area. Whatever force we are applied on both side, it is equal, and that force upon cross sectional area will be the stress. Strain is nothing but, consider this total length, initial length is L0, that shown by red color, and we are applying the tensile force so that that length L0 becomes L, that is nothing but its elongation will be E. Final length minus initial length, the difference we will got E, that elongation. Therefore strain will become, strain is represented here, it is wrongly represented, it is represented by epsilon. So strain epsilon is equal to elongation divided by its original length, and elongation you can find out by final length minus initial length. So this is regarding stress and strain. All of you might know this stress and strain. Now for performing the tensile test on the metal, you require the UTM machine, that is nothing but a universal testing machine, or that machine is also called as a material testing machine or material test frame, or a hydraulic machine for tension and compression test. All the names are same for one machine, that is UTM, universal testing machine. The name itself says that on same machine we can perform the tension and compression test. Both the test can be performed on this test. While studying the compression test also we will see this kind of machine, that is UTM machine. Here also for performing tensile test we require this universal testing machine. So in this machine which is applied in a tensile force, this machine applied tensile force to the component. So consider here in this machine, whatever this upper portion is there, in that upper portion the space for tensile specimen is there. In that, movable crosshead is there and one upper crosshead is there. Upper crosshead is fixed, movable crosshead can move along these arms. So in that specimen is fixed between this movable crosshead and upper crosshead, so that we can after moving this movable crosshead in downward direction we can apply the tensile force on that component or on that specimen. Similarly, for the compression test, one bottom table is there and upper movable crossbar head is there. So component is placed here for compression test in the table, and for tensile test component is placed between the movable crosshead and upper crosshead. So this machine in this machine we can apply the tensile force to the specimen, and then we can measure the force and also the elongation also. So here some new universal testing machines are there, computerized universal testing machines are there, which can give directly what amount of load you are applying, because these are hydraulic universal testing machines. Directly we can find on the computer screen what amount of load we are applying and what amount of elongation is there in your specimen after application of load. So these arrangements are there in universal testing machine. This machine usually uses the hydraulic cylinder to create the force, and the applied force is determined by the system pressure, which can be accurately measured, and it is shown here in the load indicator. So this is the universal testing machine required for testing the tensile test, and the specimen which is spaced between the upper arm and lower arm can be made up of two kinds, that is a flat test piece or a round test piece. You can make it in the form of a round cross section or in the form of flat cross section also, or a rectangular cross section also. So whatever distance between the 2 points here it is there, that fixed distance is nothing but a gauge length. That gauge length and the cross section area of this tensile test specimen is having specific length. That length is called as a gauge length, and the portion beyond this gauge length is fixed in the upper arm and lower arm of the UTM machine, and the diameter of cross sectional area is also fixed. So the dimensions of this tensile test specimen are fixed and predetermined. After this, that is placed in between the upper arm and lower arm, and load is applied on that UTM machine, and during application of load whatever amount of force applied and elongation can be measured, and it is represented in the computer. So after knowing the force, cross sectional area and change in length, you can find out stress and strain with the change of load. So after calculation of stress and strain, that calculation will be done by computer and it is shown in the screen only. So that stress strain diagram can be drawn. So that stress strain diagram can be plotted, and the diagram gives us the behavior of the material and the material properties. By understanding this stress strain diagram, we can find out all properties of the metal. Next, each material produces a different stress strain diagram. The stress strain diagram produced by each material is generally different. For a brittle material, it is having certain different stress strain diagram. For ductile material, it is having certain different stress strain diagram. So here one of the stress strain diagram for the ductile material is shown, in which you can observe on x-axis strain is there, that is epsilon, and strain is equal to E upon L0. E is nothing but an elongation or a change in length, divided by L0 is initial length. On y-axis stress is there, that is force upon cross sectional area, F upon A. So with the increase in force, nothing but with the increase in stress on the component, how the component or material behaves, that means what amount of changes in length will occur, that graph is shown here. Understand, whenever under UTM you are applying load, tensile load on the component, that length of that component is going to be increased up to certain limit. So here from 1 point to 2 point, that length of the component is going to be increased continuously, and above this stress, uh, if you increase that, the strain will not be remaining the same, it is going to be changed. So whatever changes are occurring, that we will see one by one in this stress strain diagram. So consider a first point, point number 1 and point number 2. Point number 1 and 2, with increase in stress on y-axis, there is continuous increase in the strain also. That means from 1 to 2 point there is a linear change in the graph. That means with increase in stress there is also increase in strain. That means with increase in force there is a continuous increase in the length. So the material will return to its original shape after the material is unloaded. That means if you are applying stress up to this point number 2, point number 2 line is extended on y-axis, and at that point we have given name called as yield strength sigma y. Up to that stress, if you apply the force on the component, there will be elastic change in your material. That means after removing the force, that component can get its original position or original shape or original length. That's why it is called as elastic region. The stress is linearly proportional to strain in this region. Stress is proportional to strain in this region. Now if you know this stress and strain at this region, we can find out one modulus of elasticity, that is capital E. It is represented by capital E, and that is E is equal to stress upon strain, that is represented here in this formula. E is equal to stress upon strain sigma upon epsilon. That A over the head 0 is there, that is nothing but epsilon, that is strain. Therefore E is equal to stress upon strain, and that is nothing but a modulus of elasticity. Now what is exactly modulus of elasticity? A measure of material. Modulus of elasticity is a material is a material's ability to regain its original dimension after the removal of load or force. If that material regains its original position immediately, then it is having a modulus of elasticity more, that E is more, that is sigma upon rho. So stress upon strain is more for that material. The modulus is the slope of the straight line portion of the stress strain diagram up to the proportional limit. So in that diagram, whatever slope of that 1 to 2 point, if you find out, that slope is nothing but a stress upon strain, nothing but a sigma upon epsilon. So if you find out this slope of this 1 to 2 line, it is nothing but a modulus of elasticity, that you can find out. So from that first region you have found the modulus of elasticity of the material. So modulus of elasticity is the measure of material's ability to regain its original dimension after the removal of load or force. And that point 2 is also important. That point 2 is nothing but its yield strength, a point after which the permanent deformation occur. That means up to point 2 only you can apply the stress, so that below this stress, if you apply this stress, that component can regain its original size and shape. Above this stress, if you applied the stress, then there will be permanent deformation in the component starts. So that point 2, if you draw it horizontally on the stress line, that point is called as a sigma y, that is yield strength of that material. So that is also important point. If it is passed, the material will no longer to return its original size and shape. So that point 2 is called as yield strength. So we have understood the two things from this stress strain diagram or tensile test: one, modulus of elasticity, and second, yield strength. Thirdly, we can understand that one elastic range means what. Elastic range means what? In a stress strain diagram, you can observe the elongation over a unit length will behave linearly. Linearly means that equation can be y is equal to mx plus c, and thus it can be predictable. Whatever elongation in the material is there, that can be predicted up to that much load. If you apply, the elongation will be what that you can predict, and according to that you can design the component in the elastic ranges. The material will return to its original shape, that is point 1, once the load is applied, once the load is removed. The stress within the material is less than what is required to create the plastic behavior, that is deform or stress significantly without increasing stress. So that is the elastic range. Next, one more thing in that region we can find out, that is a resilience. First thing, we have found modulus of elasticity, secondly yield strength, and thirdly resilience. So what is the resilience? It is the total energy absorbed by the material during its elastic deformation. So whenever elastic deformation is from 1 point to 2 point, beyond this there is a plastic deformation, and up to yield strength, that is the elastic deformation will be there. So up to elastic deformation or elastic load or yield strength point, area under this curve will represent the total energy absorbed by the material, and that total energy absorbed by the material is nothing but a resilience, isn't it? It is the area up to elastic load in the load extension diagram. So high value of this resilience is necessary in certain components like shock absorber, springs, or diaphragms. In shock absorber, you are applying the high amount of load suddenly, that means stress is applied in high amount, so that after application of stress, that component should regain its original size and shape immediately. So that ability or that area must be larger in that case, so that it can regain its original shape, and so that energy up can absorb that material in larger amount. So this is the resilience. That third thing we understood from that point 1 to 2 from the stress strain diagram. Next, point 2 to 3. So from point 2 to 3, you can observe here in this diagram, once you applied the stress, increase the stress from yield strength, that is sigma y, to sigma uts. Here from sigma y to sigma uts, here you have increased the stress. Once you have increased, then there will be change in strain in this fashion, like this, from 2 point to 3 point. It is not the linear curve, so during this region from point 2 to 3, we are calling this as a plastic region. Why? If the material is loaded beyond the yield strength point, that is point 2, the material will not regain its original size and shape after unloading. It will have some permanent deformation inside that. If the material is unloaded at point 3, the curve will proceed from point 3 to point 4. The slope will be as the slope between point 1 to 2. Now see here, whenever you have increased the stress from this sigma y to sigma uts, then the strain will change like this. Therefore stress strain curve will be from point 2 to point 3. There will be no any linear change. It will continuously increase in small amount. So from 2 to 3, this kind of curve will observe, and at point 3 there will be maximum possible amount of stress that you can apply. That's why it is called as sigma uts, that is ultimate tensile strength. And from third point, if you unload that load, then it will not regain from third point to 1 point. It will regain its size and shape from third point to fourth point. That means there will be permanent change in length, that is from 1 to 4 point. That is nothing but strain. that much strain will remain in the component itself, whereas this 3 to 4 line is exactly parallel to 1 to 2 line, exactly parallel. The slope of 1 to 2 line will be same as that of 3 to 4 line, but there is permanent deformation occurring in the component. In this plastic region, the distance between point 1 to 4 indicates the amount of permanent deformation. So from this 3 to 4 line, we can find out this plastic region. We have understood what is the plastic region for this kind of material, and in that plastic region we can find out one thing called as a toughness. So it is the total energy absorbed by the material prior to the fracture or failure. This energy is the sum of elastic energy and plastic energy. So after this third point, one more point is there next. If you increase again stress beyond this sigma ut, there will not be any up to sigma ut you can apply the stress. Beyond this, without application of stress, there will be deformation or there will be change in length of the component. From 3 to 5, there will be a necking of that component. Necking means change in the dimension, sudden change in the dimension, and from 3 to 5 point there will be continuous decrease without increasing strength in the strain. So from 3 to 5, at 5 point there will be breaking of that component, there will be sudden breaking of that component. So 1 to 2 is elastic region, 2 to 3 is plastic region, and 3 to 5 there will be necking of the component. Necking means decreasing the dimensions, sudden decreasing the dimensions of the component. After necking, at 5 point there will be fracture and breaking of that component. So toughness is what? From breaking point to this first point, from fifth point to first point, whatever area under this curve is nothing but total energy absorbed by the material, and that total energy absorbed by the material up to the fracture point is nothing but toughness. Now total energy of the material absorbed up to point number 2, that is yield point, is we have called it as a resilience. Up to point this yield point or elastic point, whatever area under that curve is we have called as a resilience, and whatever area under curve from point 1 to point 5, that is up to the fracture point, that area or total energy we have called as a toughness. This energy is the sum of elastic energy and plastic energy. This totally we are calling it as a toughness. So you can find out the toughness. If you calculate this area under that curve, you can find out toughness of the material also, and previously we have called as find out the resilience of the material also. So these things we can find out. Again, one concept called as a strain hardening also we can find out from this stress strain diagram. So if the material is loaded again from point 4, the curve will follow back to point 3 with the same elastic modulus. Now see in this diagram, whenever you have applied load from 1 point to 2 point, elastic behavior it has done. From 2 point to 3 point, it has done the plastic behavior. And from 3 point, if we unload that load, then from 3 point to 4 point it has come. So there is permanent elongation from 1 to 4 point it has occurred. Now from 4th point, if we load it again that component, that curve will behave like this, 4 to 3 point, and then it will change further. So from 4 to 3 point there is a which kind of plastic or elastic behavior? There will be the elastic behavior 4 to 3 point. Now here that 3 point will become the yield strength of that material now, because from 4 point to 3 point we are again loaded, and up to 3 point that will be the yield strength in this case. Now that means yield strength you have increased. How you have increased? By raising by raising the yield strength by permanent straining the material, because from 1 to 4 point there is a permanent strain, and due to that permanent strain there is an increase in the yield strength of that material. So this is called as a strain hardening, isn't it? The material will show now the higher yield strength point, and that yield strength point will be 3 now. Instead of 2 it will be 3 now if you load that from 4 point to 3 point. That is called as strain hardening. This concept is also can be found by using tensile test. Tensile strength, now whatever point 3 you have seen, that up to 3 point you can give or you can apply the stress. Beyond this, if you apply the stress, there will be immediate fracture. So what is the tensile strength or what is the ultimate tensile strength? The largest value of stress on the diagram is called as a tensile strength or ultimate tensile strength. From this diagram, that 3 point is the largest point. If you increase the line from 3 point on the y-axis, there you can find out sigma UTS, that is nothing but ultimate tensile strength. It is the maximum stress which the material can support without breaking. Beyond this, if you go, there will be breaking of the component immediately. So the tensile strength you can find out by the formula maximum load upon the cross sectional area. At the tensile strength only, that is sigma ut, maximum load will be there. Beyond this you cannot go for any kind of material. So maximum load is the highest point on the graph. Here maximum load will be at this 3 point only, that is at the sigma ut. Now you have understood that from 1 point to 2 point there will be elastic deformation, from 2 point to 3 point there will be plastic deformation. Now 2 point is called as yield strength, 3 point is called as ultimate tensile strength. Next, point number 5, that is a fracture point. If the material is stressed beyond or stretched beyond point 3, the stress decreases as the necking and uniform deformation occurs, and fracture will occur at point 5. From 3 to 5 there will be necking started, and after necking there will be immediate fracture and breaking of the component. So breaking or rupture stress we can find out from this point number 5. So at point 5, the maximum amount of stress that can be applied before rupture or before breaking occurs. The material fractures in the necking region where the material reduces its diameter as the material elongates. So at point 5 we can find out the stress, and that stress is nothing but a rupture stress. That stress we can call as a rupture stress. So 3 stresses or 3 strength we have found. At point number 2 it is yield strength, at point number 3 it is ultimate tensile strength, and point number 5 there is a breaking or rupture strength. So in actual practice, whatever diagram we have seen, it is like this. It is for A36 type of steel. Here you can see the elastic region, very straight line. After that there will be small up and downs, that is a plastic region. After that yield point, then there will be strain hardening, there will be continuous increase in the yield point. After that there will be ultimate tensile strength, that is a maximum point in of stress in that diagram. After that there will be formation of necking, that means there is continuous decrease in stress, and finally there will be breaking point. This kind of actual diagram you can find out on the UTM machine. It is generally represented by this kind of stress strain diagram for better understanding. Next, stress strain diagram for the brittle material. Now for the brittle material there will be only one curve you can observe, that is in second diagram you can observe one straight line from one point to y point, and after y point immediately after application of stress there will be ultimate tensile stress and fracture point immediately will be there. There will be no any small change such as a u to a y to u point, u to f point. There will not be any necking in the brittle material. The rupture occurs along the surface perpendicular to loading plane. These brittle materials are examples: glass, stone, again normal concrete or aluminum. So in there you will find out different kind of stress strain diagram in which there will not be too much uh, strain hardening, or there will not be ultimate tensile strength point, there will not be any necking formation. Immediately after that elastic region the component will get fail. From this diagram also, if you plot a diagram for particular metal, you can easily judge whether that material is brittle or ductile. If you get first kind of diagram, it will be a ductile material. If you get this second kind of diagram, you can get the that material is brittle material. So this property also you can find out by using the tensile test. Now what are the benefits of this tensile test? uh, the data produced in the tensile test can be used in many ways, including to determine the batch quality, to determine the consistency in the manufacturing, to aid the design in the process, to reduce the material cost, and to achieve the lean manufacturing goals. All these things we can find out if you find all these properties by using tensile test. So this is regarding today's lecture. Thank you all. In next video we will find, or we will see the actual procedure for finding the different properties by using tensile test. We will see one video. Thank you.